So let me consider a wall. And let's imagine this is just a flat plate. All right. So a flat plate boundary condition has the Blasius boundary layer profile, which grows. So if the boundary, oh, I should be using red for the real flow. So let's say this is Blasius boundary layer, and the Blasius boundary layer has grown. It does not grow in the x direction. The velocity outside is the same, but it grows in the y direction, right? Okay. Now, what is the y velocity here? Let me draw a streamline that connects. No, let me don't do that. Let me draw a streamline that is exactly parallel to the flat plate. Not streamline. Let me draw a control volume whose upper boundary is exactly parallel to the wall, and its lower boundary coincides with the wall. Right. Okay. So my question is the following. What is the velocity of the true flow field at the boundary? Especially, I want to consider the conservation of mass, right? What is the component of the true velocity orthogonal to the boundary of the control domain at the upper surface? It's equal to UE, right? So the x velocity here is UE, right? But there is no contribution to the mass flux by UE. Is there any contribution orthogonal to the wall? There is. Why is the case?
Because if you do like a conservation of mass, there's more mass coming in on the left side of the control, and then there's going out the way.
That's right. So we have two similar velocity profile over there, but if you extend it up further, you can see the boundary layer at the left contains more mass flux than the boundary layer at the right, right? The boundary layer has grown, and this is the defect, has also grown, right? The defect I've drawn is also similar, because the boundary layer profile is similar. So, therefore, the total integral from 0 to, let's say, ye, the edge of the boundary layer, of u velocity dy at the first x1 is greater or smaller than the same integral at x2. I'm only considering the x directional velocity. It's greater. And the reason is because this velocity can be written as the same integral of ue dy, okay, minus the same integral of ue minus u times dy, right? This is what this integral is. I'm just adding a ue, subtracting a ue. And the first part of the integral is the same no matter I'm at x1 or x2, because I'm integrating to the same ue, right? Remember I said the top of the control volume is parallel to the wall. But this is the defect. That's what I call the defect. The difference between my edge velocity and the velocity inside the boundary layer. This difference is what I draw as the shaded area, right? And starting from x1 going to x2, the x content, the x dimension of this defect did not grow. It's always UE. But the y dimension of this has grown because the boundary layer has grown. Therefore, the area has grown proportionally to the thickness of the boundary layer. So this is greater than this. That is, the incoming mass flux is greater than the outgoing mass flux. That has to be balanced by the difference between incoming and outcoming mass flux in the vertical boundaries, right? In these two boundaries. And what is the mass flux across the wall? 0, right? That means the mass flux over here has to be non-zero, yes, but towards which direction? Up or down? Up, right? More mass comes out of here and less goes out of here. The remaining has to go out through the top. Okay, so basically we proved in this case that for a Blas's boundary layer, the velocity here has two components. One is UE in the wall parallel direction, and also a non-zero, positive non-zero in the wall normal direction. Okay. Now consider what is the UI, the inviscid equivalent flow. UI has to be equal to U outside the boundary layer. So at this point, at the top of the control volume, my UI should be exactly the same. It should also go parallel towards the up, right? X component should be UE, Y component should be positive. And what should UI be inside the boundary layer? What should the X directional velocity of UI be in the boundary layer? Can it also have a profile like this? Remember, use Bernoulli's, right? I mean, UI satisfies the inviscid flow. Use Bernoulli's. It should be irrotational, exactly, right? It should be irrotational, and here, such a velocity gradient has a lot of vorticity in it. So, if the flow has to be rotational, what should be the velocity? What should be the X velocity inside the boundary layer? Huh? Constant, right? Almost constant, right? Any non-constant in the X directional velocity has to be somehow balanced, right, by the variation in the Y velocity when you travel along the X direction in order for me to have zero vorticity. And because I know that the X directional velocity dominates, my Y velocity has to be in the boundary layer is much smaller than the X velocity. So the X velocity should be almost constant. Therefore, the X velocity of the inviscid flow should have a basically constant velocity profile, right? And also the velocity profile here is also constant. By constant, I don't mean exactly constant because there are some variation in the Y directional velocity. But the resulting variation has to be much smaller. The resulting variation in the X directional velocity has to be much smaller than the variation in the red, the true velocity profile. As a result, the imbalance between the mass flux in the inflow and outflow of the inviscid equivalent flow has to be much less than the imbalance of the true flow field. So, for the inviscid equivalent flow, can there still be no mass flux across the wall? Okay, we said there is a mass flux out of the top boundary of the control volume because the red and green has to be the same at the top wall. And the imbalance for the inviscid velocity, the green velocity, through the left and right has to be much less than that of the true velocity. So, there has to be flow going across the wall at the bottom, right? In which direction in this case?
Into the control volume.
Into the control volume, exactly. So the green velocity has to go up at the wall in order to balance the upward velocity at the top of the control volume. Okay, you can think of the green velocity as some kind of extrapolation of the velocity outside the boundary layer. And because the velocity outside the boundary layer is it's smooth, almost constant relative to the thickness of the boundary layer, the velocity at the bottom of the wall is practically the same. X velocity is almost UE, and Y velocity is almost the same as the wall normal velocity of the streamline outside the boundary layer. All right. So this is the inviscid equivalent flow. So basically, the velocity here is an extrapolation of outside velocity, in the sense that because the velocity profile here is not exactly tangential to the wall, is not exactly parallel to the wall, the velocity at the wall can also not be parallel to the wall. So the velocity profile is like that.